To those on Zoom, I'm Roger Blandford, and I've been asked to chair this session along with Sean McWilliams, who I hope is also on Zoom.
Yep, I'm here. Hi.
Okay, hi. There was a request to make this more interactive than some of the other sessions had been, more of a conversation. And the last one, I think, worked very well, and I'm trying to emulate that. I got a lot of slides, as you probably imagine, and some of these, you know, are whole talks, really. So what I've tried to do is take the topics that I was allocated and then received, and some of them I inherited from Julian, because he didn't get to the end of his session, and sort of put the focus less on what has just happened and more on sort of meta questions, which can be illustrated by the material on the some of the detailed slides I've been sent. So, and I'm going to ask for help in doing this. So I think I've got here something like 7 questions. I won't read them out, but they're sort of meant to be provocative. And the intent here is, as I say, to encourage a conversation rather than listen to the wisdom from the rest of us. I'm not expecting to get to the last one, but if we do, we'll get there, but we'll get as far down this list as we can. So let's start off with the first one, which is, I've called, it's to do with, whether or not 2-dimensional models of this are useful and adequate, or whether everything is really 3D nowadays and should be. And well, stars and this themselves went a long way in 1 dimension, so there's no reason why it can't be very useful still to do 2D modeling. But some people think that really you're missing most of the physics by not going to 3D, or as Alberto and I decided, we should call this session now 2D or not 2D. So Alberto is going to come and help me, and I should say his involvement in this is that he's the first name on the first slide I was sent. But he's going to come up here and help me.
Can I do it from here?
You can do it from there, yes. But we know what you look like. Okay. So you're responsible for this very expensive computer simulation shown here at the bottom. So maybe you could just talk us through what the issues are, you think, and then encourage others to protest.
Right. So this is going to be very provocative. First of all, not for the audience, but also for myself, because I did not make any of those. So whoever sent you that slide,
I don't know.
It's Julian?
Okay,
Julian. I didn't make any of those expensive simulations. So I guess my only fault there has been like the first name over that slide, right? So that goes back to you. So I guess I've also been one of the maybe more vocal in this conference in advertising the importance of the 3rd dimension. Yeah, so certainly 2D simulations, as Roger said, are very useful to understand the problem and also to advance our understanding of the problem. And they are definitely less expensive to do, okay, than 3D. But of course, they force you into this. So especially when you want to study disk, let's say mini disk interaction, what happens to the streams and so on and so forth, whatever. When you shock back to the disk, you're forced to stay in the plane, right? And things can go anywhere. So certainly there are things there that are probably, it's probably better to check in 3D, even, without including, I'm not talking about, misaligned disk or including radiation, including field, including anything, right? Just the dynamics. Adding a 3rd dimension, especially, well, in any case, actually, I think it's a step that we need to do in order to fully trust the results of the simulation.
So let's ask a flatlander if they will self-identify as to the value of the 2D simulations for observers. Does anybody want to speak to that? Okay, great.
Observations are in 2D.
Oh, good point. Although there are some who would say no.
But if you're at that radial velocity.
Mostly kidding.
I think an obvious one is to try to understand.
Can you identify yourself, please, just for the people on Zoom?
I'm Flatlander Dan D'Orazio. And I would say that one useful piece of the 2D simulations, as Alberto mentioned, is to be able to try and understand try to understand what happens when we go to 3D at a better level, right? To run parameter studies and understand the physics in the 2D case for thin disks, so we can get to the 3D and add the physics that's closer to what we'll observe. And Phil and others have points.
Yes.
Hey, I'm 3D enthusiast Philip Master, but I escaped to circumbinary disk physics since I hoped I could do some 2D simulations. Since I've been advocating heavily for 3D and core collapse supernova and neutron star mergers, but I think one thing that we've been missing so far is maybe identify which physics actually do need the 3D, right? Like we can understand the physics that is happening, so we don't have, I mean, everyone agrees, I think, that we want to do 3D for everything all the time, but we obviously can't since it's too expensive. So we can identify, though, where 3D would be most valuable and then kind of understand how that can guide us in doing our 2D simulations better.
Okay, here's another version, of course, the sloshing, and obviously warping in precession. So we've got two slides here. That's a movie. So let's move on to that one. Anybody want anyone? I think Mark Avara, you're here. Is that right? You're one of the people. I'm not sure who owns these, but would you like to speak about? Obviously, I mean, no one's going to disagree that this is a three-dimensional phenomenon.
Sure. So I don't own this particular simulation, but I have the same group, and it's very similar to what I'll be presenting tomorrow. Yeah. So there may be two 3D effects that I think are very interesting and have a real difference between 2D and 3D. One would be the sloshing, which you have in cavity evolving 2D simulations, but what I'll show tomorrow is that there's actually a lot of vertical structure in the sloshing. You can have material from the two mini disks that just pass across each other. The other is, of course, all of this interaction with the binaries happening at the inner edge of the circumbinary disk, and there's a lot of turbulent vertical structure that governs how the material falls into the streams.
Okay.
Could we hear from some people online just in case we've missed?
Can somebody help alert me to who's got the hands up? Okay, fantastic. Zin, you.
Please go ahead.
Hi, I'm an observer, so I appreciate both, obviously. And I think the answer really depends, as we all just already discussed. One thing that I can think of for 2D to be particularly useful is if you want to understand really the long-term evolution. So to be able to really evolve the system for a long period of time. But obviously for a system that you cannot just for it to be in a flat land, like you have to look at 3D. I don't want to circle back to the previous section, but perhaps I think OJ287 is one example where you don't have like things happening in a plane, but perhaps it'll be useful. I don't know if there's already a tailored model to the system. I mean, in terms of the dynamics, but it's a 100:1 ratio binary in a highly not coplanar plane orbital configuration. So I'm curious to see what 3D models will have to say.
Okay, thank you very much, Zin. Haiyang Wang.
Oh, hi. I have a question on 2D simulation actually, because as you know, for dual AGN, or say a binary supermassive black hole, we expect the accretion flow around them should be very hot. But in 2D, our temperature prescription looks oversimplified, or even some deviation occurring at the mini disk. So I'm wondering wondering, perhaps we should do some modification to the temperature profile when we are doing these 2D simulations.
Okay, temperature profiles in 2D simulations. That's a good suggestion. Julian, I think you want to make a quick comment.
Okay. I want to put a caption to that slide. Understand it.
Yes.
This is a vertical plane.
This is Julian Krolik speaking.
Yes, there's a caption for this slide that Roger's showing. It's actually one that was made by Mark. It's a vertical slice whose normal is the line running between the black holes. So what you see here is the velocity of this sloshing motion. You can see that it's into the board in the orbital plane. It's out of the board above and below the plane. So if you now flip back to the previous slide.
That one?
There, right. The animation showed just a cut in the plane. And so it didn't capture the entire dynamics of that motion of mass between the two mini disks. It's potentially interesting because if the binary has a non-even mass ratio, this simulation is Q equals 1, so there's no net flow, but there could be net passage of mass from one to the other via this mechanism, and that would change the evolution of the mass ratio. The other panel in that slide shows a real observation of a stellar system with exactly this going on.
Okay, thanks very much, Julian. Okay, one more. Yeah.
Hi.
Yes, got it. Okay, great. Go ahead.
Megan Newsom,
Megan.
student observer here. How are we supposed to see that sloshing? No, like as an observer.
How was an poor observer supposed to do?
Really?
Let's not linger too long on this. We've got a long list and people are going to get hungry. Okay, there we are. The one before. Okay.
One on the left is real big.
Oh, I see. Thank you.
And
okay,
perhaps
good.
Manuela can say something on that.
Okay, yes, all right, quickly.
Really quickly, since the question, I couldn't hear Julian answering that question, so maybe I'm going to repeat it, Julian. I'm sorry. But so the sloshing is related to the mini-disk physics, and the mini-disks are related to the streams, and everything is all related. So it's not that, it's a single aspect that is going on, the sloshing disconnected from everything else. It's all connected together. But one more thing about motivating 3D, well, it's just if you add spins, spins might not be perfectly aligned, and might have, so therefore introduce some interesting structure in 3D. And additionally, jets, we haven't talked a lot about jets, but jets, it's something that I think would require us a 3D. So, okay, I'm gonna just land here because I know we are over time.
Okay, can we move on? I think we should probably move on in the hope of getting some of this. So this is one that came from Sean McWilliams, and this is the question as he framed it. Sean, why don't you take over?
Sure. So, right, there's a host of observed phenomena that are posited to possibly be single black, AGNs or intermediate mass black holes. So, quasi-periodic oscillations and overtones of those, and high energy cosmic rays and ultraluminous X-ray sources, and et cetera. And to varying degrees, people have explained these with black holes accreting, single black holes accreting, and this is very much to stimulate discussion. I don't claim to really have much insight into it. I just would like to know the answer. Sort of what role would binarity play in these? Would that manifest? Right, so the QPOs presumably are not due to the fact that there's a binary, or they might be, right? The structure in the disk. How does a binary affect that structure in the disk? And the main question would be, what physics are we missing, or would we need to include to try to accurately tell observers, well, for this phenomena, this would be indicative of a binary versus a single black hole.
Okay, thanks. Before you all give the complete answer to that question, we've got a second contribution on this topic from Kimi Hayasaka. So you want to just say just a very few quick words.
Yeah, so this is a completely different topic from binary black hole. But I hope I will give something inspiring for high energy particle emission from merging binary black holes. And very recently, we found that 3 TDs are likely or unlikely to associate with ice cube high energy neutrinos. And then interesting thing is these 3 TDs share common properties like 6. And so very strong optical UV luminosity, but weak X-ray and weak radio emission with strong dust echo TDs, and then the peak of the luminosity, UV luminosity, dust echo luminosity, optical luminosity is almost Eddington luminosity. And then black hole mass is 10 to the 7, and there is no high energy gamma ray signatures. And there is a neutrino arrival delay from the peak of the optical UV light curve. And these 3 are, okay. Yeah. So anyway, I'm open to discuss about the high energy particle emission from binary black hole.
Yes, the connection with TDEs is obviously a good one, and one that can be taken offline, I think. Now, does anybody have any answers to Sean's questions? Sean? Well, I know what it is, but you say. Yeah. He wants ECR disambiguated.
Crazy, ridiculously high energy. It's like the
extreme energy cosmic rays. I think it is ultra high energy. Is okay. Yeah.
Like the EEFT, just really.
Question over there, Mark.
Oh yeah, just a comment and maybe a hopeful one. So in the era of LSST, you know, if we see real good analogs to the low frequency QPOs or even higher frequency QPOs, then seeing 2 of them in one source, I think would be an interesting indication, maybe of 2 disks, maybe 2 mechanisms of whatever the mechanism is, even if we don't know exactly what the mechanism is, which we still don't.
Right. That's great.
Bhupendra, you had another comment?
Comment quickly. Great.
Yeah, so this is about the QPOs on, say, any black holes, either low frequency or high frequency. If there is a binary, I believe that it will alter the mass accretion rate. That would create mass accretion rate fluctuations. So it should imprint on the variability, because after all, it's the flux which will be varying due to these binaries, especially for low frequency QPOs.
Okay, that's great. Thank you. Let's move on to Sean's second question, which is the importance of spin. Sean, and I've got you. I think I've got it in the slide. There you are.
Yeah. So right, the binary embedded in a disk, if it's a pair of black holes, they could have spins. Back when really large recoils and numerical relativity were all the rage, and people were trying to explain that they don't happen, that at least for comparable masses, the argument was, oh, maybe the spins align with the disk. But then you have systems like OJ287, more extreme mass ratio systems, where presumably that was a circumbinary disk, and but the smaller object is processing and plopping through the disk, and the disk isn't apparently doing much of anything in response to that. So my question is, how well do we understand the role of spins and how they influence the disks, and what would we need to do to try to better understand that with simulations
So this is Laura Blecka. So I cannot answer this from a simulations perspective, but at least not from the scale of simulations we're talking about here. But my former PhD student, Mohammed Sayeb, did try to model black hole spin evolution in post-processing using Luke Kelly's binary and spiral models and based on illustrious data, and basically used a simple timescale argument to look at the time the binary evolved through the gas-dominated phase of hardening versus the naive timescale you would expect for spin alignment in a gas disk. And we found that with conservative assumptions, there's a minimum of 10 to 20% of black hole binaries that would be misaligned when they enter the gravitational wave dominated phase. And with less conservative assumptions, that could be up to like 90%. So that's a very different scale than what we're talking about here.
Right, that's interesting, yeah. Okay, looking at the clock, I'm going to go relentlessly forward to the next topic, is that many people have remarked that they feel sorry for the planets which have been muscled out at this meeting by stars and especially massive black holes. And so I'd like to give planets their day or their 5 minutes. 5 minutes. I think this is worth lingering on. This should be quite a long discussion. And Simone Seppi, Daniela Sender, and Cristiano Lagarini kindly agreed. I'm not sure whether all three are here, but they kindly agreed to lead this discussion. So you come up front.
Okay.
I mean, all three of you should come, but you should. You may have one spokesperson. But it's your question, and here it is. Have I got it there? No. There it is. Yeah. So you're on.
Here we completely changed the scale of the problem. So we are studying what's happening in planet-forming environments. So recent observations are telling us that planet formation is already underway in young systems, where when the disk is still embedded in the molecular cloud, and there are a lot of dynamical interaction between different protostars. And so in these environments, the role of stellar multiplicity is really important. And so we are asking if planet formation is easier or not in circumbinary disks and in multiple systems in general. And so there are reasons to say yes, because if we have a multiple system, we basically break the spherical symmetry of the system, and then there are a lot of phenomena that can occur, so such as warps. The binary can create spirals inside disk. The disk can break. There are quasi-Lidov oscillation onto the disk, and these phenomena can create dust traps, so can collect dust in some part of the disk, and if dust is collected, the planet formation is favored. And but there are also other reasons to say no, because I mean, in a multiple system, the orbital stability of planets is more difficult, and then in particular in circumbinary disks, the radial drift is more efficient. Basically, the radial drift is an effect of the aerodynamical coupling between gas and dust in protoplanetary disks. So because of the coupling, the dust is pushed toward the central object in a very short time scale, and so planet formation should be very quick to take place. And then another observational problem is that we do not observe a lot of circumbinary disks. So, I mean, this can be a problem. And I don't know if you have something to add.
Well, also the yes point could be a no point, because we have to study the efficiency in the growth of dust in those traps, because it really depends on the relative velocity between the grains. So it's not sure that they help planet formation. And in general, we would like to ask what do we need to constrain planet formation in multiple systems? So to answer to check if the yes or the no weights more. And so maybe more statistic of very young systems, and so what are the problems in observing these systems, and also more statistic of formed planet around multiples, so that we can constrain something on the physics that formed these planets. So yeah, we can start the discussion.
Okay, and anything else you want to say, or should we bring it out to the floor?
if someone has something to say.
You want to say something? No, that's everything. Okay, well, thanks very much for that lucid introduction. Let's open it up to the floor. Steve. Oh, sorry, here first, yes.
Josh Calcino here from Los Alamos. I have two things to add. On the yes side for the induced dust traps, going back to the circumbinary lump thing that we see in circumbinary disk simulations of AGNs, I've shown in some previous work that you can azimuthally and radially trap dust in these lumps in the protostellar context. So that could help facilitate planet formation potentially. And I have an opinion about the number of circumbinary disks is low compared to single stars. Yes, that's true, but the disks that we seem to think are more involved in the protostellar context, i.e. the transitional disks, tend to overwhelmingly be Herbig stars. So massive stars, which are, as we all know, much more likely to be in a binary system. So I have a thought that potentially a lot of these are circumbinary disks and we haven't spotted the companion yet because of large mass ratios or weird orbits or something.
Okay, great. Thanks, Josh. Steve, I think.
Yeah, just in clarifying that it is true that not all transition disks are binaries. It is not true that they're all undetected binaries yet.
Good.
Yeah, my understanding of the data on circumbinary planets is that they're consistent with the idea that their frequency is comparable to the frequency of planets around single stars when you account for all the observational biases, which there are enormous numbers. So the efficiency is not enormously reduced. I think most people would. That's what the people working with the data have suggested. So I think there is not a great destruction of the planet formation process, but there are only 10 or 12 circumbinary planets known, and it's a real statistical challenge to account for all these biases because detecting a circumbinary planet by Kepler or TESS involves a certain alignment between orbits and so on, but that's what my understanding is of what the data is telling us about the circumbinary planet formation.
Is anybody optimistic about Webb seeing some large separation planets circumbinary?
No, I'm not. But sorry, I wanted to point. There's people online.
Yes,
so let's go.
Go for it.
Judith, Raja, Roman.
All right, thank you. So I think we also have to distinguish whether a P type or S type, what we are talking about. So whether we have one disk around the two binary together, or we have disks around each individual binaries, because my understanding, it's different than the previous speaker, so that we have solo observations, because even though might be the planet formation proceeds the same way, and we do form planets, but we more likely lose them. Either they get ejected from the system or or migrate into the stars. The tides are much stronger. So I think we don't keep them. And that's the reason why we don't see that many in binaries in terms of observations of planets. And I think we should listen to the data, because we know more than about 5,000 extrasolar planets today, and only a handful of those are in binaries. So I think that shows really that we cannot maintain the planets around binaries because of the strong tides. That's my understanding.
I'll just to answer your first one. I think they were talking about circumbinary planets, so that which is I think maybe a slightly different population. But go ahead. I think Raja, you were next.
Yes. So I was going to mention some stuff that I did in my PhD. Was motivated because a few of the circumbinary disks that we observe are really old compared to what we think a typical protoplanetary disk lifetime is. So we think protoplanetary disks should disperse in a few million years, when we see like these circumbinary disks that are sometimes even greater than 10 million years. So I was looking at some disk-bearing stars and star-forming regions to see if the multiplicity of those disk-bearing stars vary from the field stars, and that could give some insight into the lifetime of disks and binaries. And I found that it was pretty much the same. And I attributed this to maybe circumbinary disks have a longer lifetime and gives a higher probability for planet formation because they live longer. So the longer lifetime of circumbinary disks kind of outweighs the shorter lifetimes of circumstellar disks in binaries, maybe. But it is curious that some of the circumbinary disks that we find are quite old, and maybe that has some implications on planet formation in binaries.
Roman, there's one last online comment.
Yes, I just wanted to bring several points. First of all, I do agree with Steve Lubo that frequency of circumbinary planets is roughly the same as the frequency of planets in other cases, which might be caused by the fact that actually the frequency of circumbinary disks is not so low, but also by the fact that they tend to be more massive, so promoting potentially planet formation in them. At the same time, I would also point out that formation of planets in this p-type system in circumbinary disks, as well as in s-type systems, is obviously very different from what's going on in disks around just single stars. That's because in the center of your circumbinary disk, you have this giant egg beater that drives the eccentricity of planetesimals very, very naturally. So for them to grow to large sizes, they need to grow in collisions, and instead in the inner regions of these disks, they will obviously be destroying each other when they collide, because the collisions will be happening with very high speeds. Moreover, I would also add that the eccentricity of the disk, of the circumbinary disk, is a very big variable in this field, because first of all, we know from the simulations that we have seen so many of today, that the binary is driving the eccentricity in the disk, and this eccentric disk obviously would affect through gas drag the motion of planetesimals, but also through the effect of the gravity of the disk, because as I mentioned, these disks tend to be quite massive. As a result, there is a strong gravitational effect, very non-axisymmetric gravitational field of the disk itself, that would affect the dynamics of the planetesimals as well. And in particular, you find very interesting things. We have done some calculations of this with Kedron Silsby, in particular my former PhD student, where we showed that you very naturally get resonances, secular resonances in the disk, where eccentricities of planetesimals can go to very high values, completely prohibiting formation of planets at these locations. So while I do think that there are a lot of similarities, there are still a lot of differences, especially close to the binary. Now, if you move out from the binary, if you go like several EU from the central region of the disk, then the planet formation would probably be much more similar to that happening in single disks. And so in that case, I would think things should be pretty much similar, and that's probably how the circumbinary planets that we see are forming. So that's my take on it.
Okay, I think in the interest of time, we probably move on, unless anybody has a very quick comment or question.
30 seconds?
Yes, go for it.
No, it was a no. It's enough. I mean, we discussed a lot.
Are you sure? Okay, well, okay, one quick comment down there.
30 seconds. I think it's important to talk about the binary separations for your circumbinary planets. The ones we see are binaries about 1 AU. Short period binaries about 0.1 AU have a dearth of circumbinary planets, and binaries that are about 10 AU, those circumbinary disks are going to be on large scales, like we don't promote planet formation. So we should be talking about the sweet spot of binaries with 1 AU, where we're talking, the physics is what we're talking about.
So, yeah, well, thanks very much, Daniel, Cristiano, and thank you for leading this discussion. So thank you. Now let's move on to the next one, which is going to be, there's plenty of physics left. Does MHD make a big difference to disk physics? And here I think we have So this is going to be, yes, Bhupendra Mishra and Scott Noble sent some on this, I think. So Bhupendra, do you want to say a few words?
Yeah, I can definitely say about it. So my quick answer is yes, magnetic field is really important for all these models, especially the very inner parts of the accretion disk. And that being said, actually, that was debate about 2D versus 3D. And if you do a 2D model, you are missing a lot of physics, not just the vertical structure, but once you add magnetic field, the things are really complicated. Like if you see the very top panel here, which is a small box inside a sketch I made on the left-hand side. So you take a small box which has a binary system inside an Asian accretion disk and seed it with some net vertical magnetic field, assuming that the disk was already magnetized, which is obvious, and evolve it. And you see the difference that the top panel is hydro and the middle one is magnetized plasma, and you already see a turbulent CBD and also CSD. The one on the top, it has a very nice spiral structure, which is being washed out by the turbulence in the MHD system. The even crazy thing is, if you see the middle panel, which is actually a 3D slice, so you take a vertical cut of the disk, and magnetic field is creating some very interesting filamentary structures. And those will be missing in the hydro model, and especially a 2D model. And if you see the lowest panel here, which is showing the magnetic field amplification, which is beta, the ratio of gas to magnetic pressure. And the whole model was started with a beta of 10,000, which means the magnetic field is really, really weak. And the powerful instability, which is magnetorotational instability, and also the net flux, which is initialized in this model, rapidly develops a very strong toroidal field. And once you have such a strong magnetic field buildup, the magnetic pressure starts to puff up the disk, and it wouldn't be the disk you expect from alpha disk model. It will be much thicker, and the accretion structure will be much different. So I believe that eventually adding magnetic field will dramatically change the CBD and the CSD evolution.
So the alpha models are not capturing a lot of the phenomena that show up in this simulation.
Right, yeah.
Right, okay, now before people address that, let's go I've got here another slide that I inherited, and I'm not sure who is responsible for it, but Scott Noble's name appears on it. So in the same spirit as before, he takes full responsibility.
Yeah, so I think that these plots are from Shi et al. 2012. So yeah, I just want to, so yeah, internal magnetic stress doesn't operate like alpha viscosity. I don't know if we need to really debate that, but yeah, so for instance, like on the if you plot effective alpha, for instance, you see it depend with radius. And at the edge cavity, it can increase dramatically. So this is Scott Noble, by the way. I didn't. Also, like often, depending upon how you implement alpha viscosity, it could just relate to R and phi stresses and not other kinds of stresses. So whereas internal magnetic stresses, you don't have to tune that or prescribe that. And also, I think in terms of the lump, I think we still need to explore really why, what are the differences there. We do see, I think, qualitative differences in the lumps that we see between viscous runs and MHD runs, and I think it has to do somewhat with how like the internal stress operates there, and how magnetic field can kind of dissipate in the lump, and that can affect how the lump manifests in those runs. And you get a similar phenomenon in viscous simulations, but it's not doesn't operate in the same fashion. So exactly. So yeah, I don't know. That's all really I have to say. But
so does anybody else, including especially those on Zoom, want to add some more comments on alpha-inspired models versus magnetic models and all the other magnetic phenomena that might well be observable, not just appearing in simulations? Anybody else want to talk to that?
While people are thinking in the Zoom, I recently did a series of models side by side, like alpha viscosity model for a stellar mass black hole, and the same mass accretion rate and the same radiative transfer, everything except one is alpha prescription and one is magnetized MHD model. They look dramatically different even in terms of observed luminosity. The alpha disk model is under luminous for a given m dot compared to the MHD model, which produces way more dissipation and leads to the desired luminosity. So these are the GRMHD model of a stellar mass black hole. So I believe that alpha model, as you mentioned, it doesn't capture a lot of physics, especially if you add the radiation.
Can I ask a question? So for those of us who don't work on the black hole case, can somebody give estimates for what is the most unstable MRI wavelength for typical disk properties? You have a microphone, Julian. I'm sure you can answer that question.
There's not a single answer to it.
Indeed, the range.
Quick categorization. There's poloidal field and there's toroidal field. Generically, when there is poloidal field, it has a faster growth rate. The fastest growing wavelength is 2 pi over the Alfvén speed using only the vertical component.
Right. So I'm just asking, what is that number in physical units for the black hole case, as opposed to, because I know the protostellar disk literature much better.
It gets tricky here even to define, because if you start with a smooth field, then you can talk about linear growth rates. But once it goes nonlinear, then you have MHD turbulence. You no longer have uniform homogeneous field. And it's not a well-defined property. I think that maybe the best you can say is that it will be stirred on a scale that's some fraction of the pressure scale height, but it's going to be a range of those, and it's going to be time variable.
Are there any issues with resolution of this wavelength in the typical MHD, the typical GRMHD simulations, for example?
There are definitely questions of resolution.
Okay.
And the rules of thumb are that in order to get the right growth rate, you need at least 6 cells per fastest growing vertical wavelength. To capture the nonlinear development at a reasonable level is more demanding. It's more like somewhere in 10, 15, maybe 20 cells per fastest growing wavelength. And that applies to the toroidal as well as the poloidal structure. That is translated in practice in simulations into probably at least a few dozen cells per initial pressure scale height. We do not know what is truly converged because of turbulence, and the real physical scales of dissipation are way smaller than the scales of interest in the disk. So the best we can do, the way those numbers were defined, is by looking for certain internal ratios in the nonlinear development that seem to plateau at about that resolution level.
Okay. Okay. Yes, Mark.
Yeah, I'll try to make it short.
Yeah.
Just a comment and a proposal, maybe. So I think in doing an alpha disk and a pure full MHD comparison in a single disk system, you might expect to get wildly different results. But in the binary system, we know that a lot of the dynamics that are driven, like hydrodynamics that produce, say, the lump, maybe are robust in both cases. So I think then adding magnetic fields, you can ask exactly which new physics, like turbulence, what is the role of that? And the proposal is that out of this conference, something I'm thinking a lot about is 2D simulations give a good coverage of parameter space that we can't do in 3D. It's just too expensive. But now we can start honing in, like right on this point in parameter space where for certain eccentricities, you drive it out versus in. and we can start doing 3D simulations around that and see if it's qualitatively or quantitatively different pictures.
Yeah, particularly around the edges of this. I imagine.
And that's even for all the planar systems.
Yeah.
I'd like to make one brief physical remark, if I could, which is that we heard a lot of discussion yesterday about orbital evolution and the delicate balance between the energy and angular momentum carried by the accretion flow and the energy and angular momentum carried by gravitational torques. And because they compete with each other, there's a balancing act there. Small effects can have a qualitative outcome, a qualitative influence on the outcome. And so the big question I would ask is whether MHD will change these flows of energy and angular momentum in the two parts by 10 or 20%, some modest adjustment, but because they're subtracted from one another, that ends up being interesting. And I think that remains an open question.
Okay, thanks, Julian. At this point, we're 47 minutes into this session. This, I think, is hopeless to even start addressing. We do have the option of some quick comments, and there are lots of slides. And so, organizers, do you wish to see more slides of results of simulations, particularly of GRMHD, etc., flows around black holes now, or postpone, or maybe drop them? I mean, we can probably do this in about 5 minutes if people follow the plan of answering a question rather than describing their simulation.
Well, tomorrow is also a sort of numerical day, so maybe we can.
And there is an open session at the end tomorrow,
Yeah.
so maybe people can think about things that we didn't quite get to for the final session tomorrow. Right now, I think, Zoltan?
Additionally, if people want to come at 1 o'clock to hear the talk on the neurodiversity, they can't bring their food in here. So we need to. They need to eat by 12:59.
So it sounds like we're shelving this. I apologize to Scott and Sasha who sent me slides, but maybe there'll be some other time to allow them to show their wares. Okay, thank you very much, everybody, especially the students who contributed.